Question 6. Figure 1 shows us a sketch of a curve C with the equation y is equal to f of x, where f of x is a cubic expression in x. The curve passes through the origin, as we can see here. It has a maximum turning point at the coordinates 2, 8, as we can see here. And it has a minimum turning point at the coordinates 6, 0, which we can see here. The first part asks us to write down the set of values of x for which f prime of x is strictly less than 0, and this is for 1 mark. Okay, so note that f prime of x we know as the gradient function. Okay, it's the gradient of the function. Now for straight lines we know that the gradient of the function is constant, it doesn't change, the steepness doesn't change. However, for a curve, the steepness of the function is going to be changing at different points depending on the value of x. So here's an example of the steepness of the curve at this point, and here's an example of the steepness of this curve at another point. Okay, you can clearly see the steepness is changing depending on where we are on the curve. Okay, so what this question is essentially asking us to do is write down the set of values of x for which the gradient of the function is less than 0. Okay, now we know that when the gradient of a function is less than 0, or when we have a negative gradient, this is represented by a line that is downward sloping. And by looking at this graph, we can see that the portion of this curve which would be downward sloping would be here. Okay, and that's between x values of 2 and 6. However, we must be careful because we are explicitly told in a question that we have turning points at these specific coordinates. Okay, and we know that these are the points where the gradient function f prime of x is equal to 0. So then of course these x values of 2 and 6 would not fall within our desired region, as we're only looking for x values where the gradient function f prime of x is less than 0. So now we can answer the question by saying that when f prime of x is less than 0, the set of values of x that satisfy this inequality are those values of x that are strictly greater than 2 but strictly less than 6. Okay, moving on to part B of this question. Now we're told that there exists a line with the equation y equals k, where k is a constant, and this line intersects C at only 1 point. And we've been asked to find the set of values of k for which this line intersects the curve at only 1 point. And we need to give this answer in set notation. So the first thing to observe is that we have a line with the equation y is equal to k, where k is a constant. So that means that this line is going to be a horizontal line that cuts through the y-axis. Now, since we've been asked to find the set of values of k, well, that suggests that there's going to be more than one horizontal line that intersects the curve C at 1 point. Now, by inspection, we can see that this horizontal line here would only intersect with the curve once. This one here would only intersect with the curve once. But when we get to the x-axis, where y is equal to 0, we can see that we would get 2 points of intersection. So everything below the x-axis would satisfy the value of k we're looking for, but not including the line y equals 0. In fact, everything between y values of 0 and 8 would cause the horizontal line to intersect with C more than once. And hopefully you can see that there is another set of horizontal lines that only intersect with our curve C once. And it's the set of horizontal lines y equals k, where k is strictly greater than 8. Okay? So these are all lines that you can see only intersect with the curve C once. So just to be super explicit, it's going to be this whole region here. Everything below the x-axis, or the line y equals 0. And everything above the line y is equal to 8. And so now we have our region. Let's write it in set notation. First, I like to start with just writing it as a simple interval as follows: the set of values of k that are strictly greater than 8 or values of k that are strictly less than 0. It's a disjointed interval, as you can see on the shaded diagram, hence why we're using or and not and. Now we can use this to just convert it into set notation. So this is equivalent to the set, and we use a curly brackets for the set notation, the set of values of k such that k is strictly greater than 8, and we represent or using the union symbol, the set of values of k such that k is strictly less than 0. Okay. The final part of this question says find the equation of C. You may leave your answer in factorized form, and this is for 3 marks. So let's try and use the information we've been given in the question about the curve to find its equation. So what do we know about the curve? Well, we know it's a cubic function. We've been told that. We can also see that by the shape of the curve. By looking at the graph, we can also see its roots. We can see that there is a root at x equals 0, and there is also another root at x equals 6. Now you are required to understand the behavior of roots for cubic graphs. And in these types of questions, I'd always recommend you start with the roots, okay? So we've been told that the curve passes through the origin, and we can also see this on the curve. When a curve passes directly through the origin, we have a single root. So we can straight away say that y is going to be equal to one of the factors, x, because we have a single root at x equals 0, multiplied by some other linear or quadratic factors of this function. We've also determined that there's a root at x equals 6, but looking at the root, we can see that we bounce off of this root. What does that typically mean for a cubic function? That means there is a double root, also known as a repeated root, at the value x equals 6. And therefore the other factor is going to be x minus 6. So we have to multiply this single factor by x minus 6. But because it's a repeated root, we have to square it. Now we've written an expression for this cubic equation which accounts for the roots. However, just on its own, there are actually infinite number of ways that this expression can be drawn. I'll show you an example. So here is one example, and here is another example, which is a lot steeper but goes through exactly the same roots. In all 3 graphs, we can see that we go through exactly the same roots in the same way. However, the steepness of the red curve is a lot greater than the steepness of, say, the blue curve. Now in both examples, we can see that each graph is either being stretched or compressed in the y-axis by some factor. And so in order for us to get the right expression for the curve C, we need to multiply it by the right factor. So let's call that factor A. Now, in order to find the correct factor for this curve C, we can use the coordinate we've been given on the curve. The coordinates 2, 8, where we have the x and the y value. And we could substitute that into this equation to find a value for our factor A. So let's call this equation 1, and subbing the value of x equal to 2 and y equal to 8 into equation 1, we get the following. 8 is equal to 2a times by 2 minus 6 all squared, and therefore 8 is equal to 2a times by 16. Evaluating the right hand side, we get 8 is equal to 32a, and dividing both sides by 32, we get that a is equal to a quarter. And so now we found our value for a, we can simply sub it back into equation 1 and produce the following equation for f of x, which is equal to a quarter x times by x minus 6 all squared. And we can leave the answer in factorized form. If you like this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.